And we're recording now. Okay, so if you go to Blackboard, under the announcements section, I think also under the class sections for session 8, we have links to the data, to the community health survey data. Actually, it's on announcements right now. I'll be adding it to the session after when I put the links to the recorded versions of it. Okay, so New York City Department of Health each year does a survey of the health of New Yorkers. A lot of it, I think, is a phone survey. You guys can go online and probably read a bit more about it. I'm going to click into it right now. You can actually Google it. If you Google New York City Community Health Survey, it'll bring you to this page. And on this page, you will find links to the actual data and the survey itself. So you can actually go onto this website. And for instance, the data that you have right now on Blackboard that is under the section for your project is the 2011 data. I may actually update that so you have access to more recent data. So if I click in here, it's going to give me the actual PDF file with the actual questions that are asked on this survey. And it's pretty extensive. I'm not sure what kind of incentives they give to people, if any, to actually answer all of these questions. And there's 10,000 or 20,000 people that they eventually randomly select and survey. Again, you might be able to draw out some information by reading more of this stuff on how they attempt to randomize the survey. You'll notice that we're going to talk about adjusted values and raw crude data, the crude data being the actual exact answers and collected data for everybody that does the survey. For instance, on cardiovascular health, they might ask one particular question they ask is, have you ever been told by a doctor, nurse, or the health professional that you have hypertension, also called high blood pressure? So they have an opportunity to respond yes, no, don't know, not sure, or they can the surveyor might put down that they refused the question. So basically, eliminating the don't know or not sure, basically people are mostly answering either yes or no. Anybody want to hazard a guess as to what kind of variable that is? If you ask a question, do you have hypertension? This is basically asking, do you have hypertension? They answer yes or no. So what kind of variable is that? Is that a numerical variable? No, you may enter it. You may enter one as a yes, two as a no, but it's not really numerical. If they actually asked you, do you know what your last blood pressure reading was, and you replied with, oh, it was 120 over 80 or something like that, that would be a numerical variable. But in this case, the question, do you have high blood pressure? Or in this case, the way they phrase the question, have you ever been told that you have high blood pressure? The answer is yes or no. What kind of variable is that? They're already answering it online. What's that? Nominal or categorical? You use the phrase nominal or categorical. Exactly. It's a category or a name or something like that. Right? So if you did, you'd say yes. If you didn't, you'd say no. Right? But there's also other variables in here where they, for instance, might ask your age. And if you answer what your age is, that would be a numerical variable. Or if they ask you specifically what your blood pressure, I don't think they do, but they definitely do ask you your age. But they may not actually ask you what your blood pressure is. Right? So there are some numerical variables here. There's some categorical variables. Okay, so now there are also some variables. For instance, this one. During the month that you were at your worst emotionally, how often did you feel sad or depressed? Depressed that nothing could cheer you up. Okay, so the categories you could choose are all the time, most of the time, some of the time, a little of the time, none of the time, and other situations where they basically didn't answer. So you had 5 choices there, from none of the time to all of the time, and a few in between. So those are categories, aren't they? But they're right, exactly. They're a special kind of category. They're ordinal. That's ordinal data. So we have categorical data that we looked at before, that yes or no, or nominal data, whichever way you want to call it. And we have a special kind of categorical data, which is ordinal. In other words, they fit into a category, and that category has some order. In other words, if they're depressed all of the time, that's worse than most of the time, some of the time, a little at a time. Now, how much of the time they're depressed is not really specified here. It's not like 3 hours every 24. So it's not something you could describe as a scalar data or numerical data. So this is a special kind of categorical data called ordinal data, where we have an order: good, better, best. Pain scale 1 through 10 or something like that. So that's another kind of. Then we also have our ubiquitous, not so ubiquitous on this survey, because the survey tends to be largely categories and ordinal data, but they do have some places where they have some numerical data. I can see if I can't find it quickly. Age. Let's see. Oh, manager and stuff. Okay. What is your age? Age in years. Don't know or not sure, and refuse our choice there. But most people answer with a number in the range of 18. Apparently, the oldest person here was 98. Okay, so they answered in a range of 18 to 98, and that's a numerical variable. Oh, you don't see it behind me. Okay, good. Are you watching it on there? By the way, hang on, guys, online. I'm just going to put this on the board behind us. You're right. I didn't bother to set this up here. I thought maybe because you were looking at the screen, I thought you might have been following me on that meeting on there.
I usually put on the screen what
Yeah.
problem.
Yep, no problem. I just kind of neglected it because there were only 2 of us, and I thought you guys were following it on there. Okay, let me just go there. And what is this? Launch application. Good. Close this now. Okay, there we are. See, okay. Let's turn the light down so you guys can see that. Okay, better. Okay, so I'm going through this PDF file that is online. That's at the on Community Board Health. I'll go backwards and show it to you in a second. But you have all these questions that they've asked are summarized here. They asked, for instance, where were you born, USA or outside the USA? That's a non-categorical variable. But then they also ask a question where you can actually identify a country as well. So you can have something that's 2 categories, USA or not USA, and you can have another question related to it where you actually identify a country. And it's a nominal variable because it's the name of a country, but there are almost 100 choices, 75 or 100 choices or something like that. Okay, and how did we get to this again? Let me just show you how we got to this again. We got to this by going to the New York City Department of Health website and going to the Community Health Survey, clicking on public use data, and going to, in this case, the data for 2013, and clicking on questionnaire and bringing up this PDF file, which actually lists all the questions that they were actually asked. We could also, while we're there, we could also actually download the data set itself. Now I'm going to click into there, and the problem with me clicking into there is that it's an opportunity to download the data in a format that is suitable for a program called SAS. Okay, we're not using that. It happens to be on the computers here. We're not using SAS, but we've actually converted this data for you for the 2011 data. I might be able to update that for you so we can use more recent data, right? But for now, on Blackboard, we have available to us. If you go into the tab for the project, there's a lot more tabs here because there's many you can't see. If you go on the tabs for the final project, if you go in there, in addition to that document, that Word document that has a description of the project and the due dates and so on and so forth, we also have the actual data itself. Here's the questionnaire. data that we were talking about. There's also a code book, and there's also the data itself in both a comma delimited format, that's a CVS, comma separated format, or actually as an SPSS file. So let me open that questionnaire, right? Notice that that's exactly what we we're just looking at for 2013, that is. Okay, let me go back and look at the code book. Now, the code book is an abbreviation of all the variables that are in those questions. So, in other words, when we were looking at blood pressure, hypertension, here's that question. Have you ever been told by a doctor or nurse or the health professional that you have hypertension, also called high blood pressure? And the acceptable answers were yes or no, or didn't answer in some form or another. And the variable name for that, which we're going to be, it's important to us because the variable name is how it's identified in SPSS. The variable name is told high BP11. So that's where we would find that in that SPSS file. So I'm going to open up that SPSS file now so we can take a look at it and find that specific piece of data. Okay, so let me start up SPSS. Okay, you guys online, are you giving this a try? If you have a computer that has SPSS on it, you might want to open up that data file that we download and open that data file that we have on board here. Okay, and if I'm going to go back here, and I'm actually going to download it to my desktop myself. I know I have it somewhere on my in one of the folders here. However, instead of opening it there, this is still the NC birth data, and instead of opening it there, I'm going to go to Blackboard, and I'm going to right-click on projectdata.sav, and I'm going to save it on my desktop. Whoops, I think I did something wrong there. Try that again. Control, save link as, and I'm going to drop it onto my desktop. Okay, give it a moment to download. Okay, I think it's already there. Right, it's basically a text file, so it doesn't take long to download. Let me go back to SPSS. Okay, and I'm going to say open data. I'm going to navigate to my desktop. And I should see an SAV file, New York City Community Health Survey 2011. I'm going to open that, and it will open in SPSS. If I'm lucky, it sure does. And you'll see that we have many columns of data. We have a column for each variable, right? So one of the variable we were looking at was that told that you had high blood pressure. Well, it might take me a while to notice the variable names are in the columns, top of the columns. So here's US born, yes or no, we know about that. I'm going to go to the variable view, and each row here represents a variable, a column in the data view. Okay, and there's 190 different questions that they asked and got answered. Okay, yeah. So, and I'm looking for, what was it again? I'm looking for number 13. Yeah, there it is. There's the good work. There's the data that we're looking for right there. I can go back to the data view, and it's the 13th column. Okay, and in fact, here it is right here. Just sort. Told you had high blood pressure. I know that, in fact, I'm going to just quick look at the variable view. The variable view is already coded so that the label actually has the question in it. Whoops, let me undo that. The label actually has the question in it. Okay, if I hover it, it may show it. Maybe not. Okay, and the value has the answer to what 1 stands for and what 2 stands for. So that means when I go back to the data view, if I turn on the value labels, it'll actually show me for person number 1 what they have been told they have blood pressure. Next person, no. Yes. Next person, yes, and so on and so forth. Okay, so I can go through all of this data. And how many people are in this study? Well, let's see. Let me see if I can't move this over and move this down manually. let's go see how many people were actually in this crude data, how many people actually were surveyed. Okay, so we have 8,792 people, right? I'm sure that there's many that like were eliminated because they didn't answer some of the questions. You see, this person didn't answer all of the questions, or for other reasons, but they certainly survey a decent number of people. This is a lot of data here. Okay, so I can actually operate on this now. Now, your choice, if you were doing something examining an association between high blood pressure and some other variable here, for instance, how much soda you drank, whether you smoked or not, those are all variables here. We wouldn't really need all these other 185 columns because you're just going to be focusing on the data that you're concerned with. So we can actually, I'll show you later as we move forward in the coming weeks. I'll show you how you can recode the data, how you can like eliminate stuff that's extraneous to you, how you can filter the data, how you can do all sorts of stuff with it. So for our purposes right now, I might, for instance, right now say analyze descriptive statistics frequencies because I'm looking at a nominal variable and say, okay, how long, let's see, when it's the 13th one down, so it shouldn't take too long to get to it. Ever been told, let's see, if I hover, it'll show me the whole question. Ever been told that you have high cholesterol? Next one, ever been told, ever been told by a doctor that you have hypertension? So that's the one we were looking at. So I'm going to move that in there. And since it's a nominal variable, I'm not going to do statistics like mean and so on and so forth. That's not going to do me any good. I'm just going to do frequencies for this one. So, and maybe I'll have it do a bar chart for me. And I'll click continue, and I'll click OK. And sure enough, it'll give me a table, and 36% of the people have been told they have high blood pressure, 63 have never been told that they have high blood pressure. You know, as I get older, I'm beginning to realize something. In the old days, right, like 20, 30, 40 years ago, right, what was considered high blood pressure or high cholesterol has gradually been getting lower and lower and lower. I think that in the beginning that my doctor considered high blood pressure anything that was higher than his blood pressure. I think that's the criteria that he used, as best I could tell. You know, and back in those days they were smokers. But we know that people are more concerned about the effects, public health effects, particularly of high blood pressure, high cholesterol, and so on and so forth. So they've gotten it's paying much more attention to it, and the threshold for an intervention has gone down. Like I remember there was a time when they would not suggest any kind of cholesterol reducing drugs unless your cholesterol was over 200. But now they're aggressively treating people whose cholesterol is well under 200, but they don't feel the ratio of good to bad cholesterol is good. So now, if you walk out of a doctor's office, if you're over 30, you walk out of a doctor's office without a prescription for Lipitor, you're in great shape. You know, because they really are treating cholesterol much more aggressively than they used to. So at any rate, so you guys, let me see, there's a question on here yet. Let's see. We're supposed to see all of that content that's in your final project folder. You should see, that's a good question. Let me go back there and take a look, make sure it's all available. Let's see if I made that available to you or not. Maybe I just put the document there. Let me go back here. Okay, you should see Biostatistics Project. You should see New York City Community Health Data. Both of those are available. This last part here, 3 steps to participating projects, not available yet. There's a task you're going to have to do going forward, like give me an idea of what project you want to do and so on and so forth. I'll make those available once we really start to talk about them. Okay, some of it I'll alert you to with an email or announcements, that you should start to consider this, and I need you to do this by a certain date. And some of it, and it'll come up as we move forward. Okay, I'll give you some project examples as you get into. It's a little premature now because you haven't really started to even think about what project you're going to do.
Like a due date for next Thursday.
Yeah, for you to choose which variables that you would like to work with and do some descriptive statistics. Like, for instance, if one of the things you want to work with is high blood pressure, by next Thursday, I'm asking you to do this analysis. Let me go to the output window and let me know. Well, gee, Tony, this population has more women in it than men, and here's a bar chart that describes the percentages, and the age distribution looks something like this. And since I'm looking in particular at, I didn't want that, I want the output window. Since I'm looking in particular at high blood pressure, well, here's the distribution of people that have reported that they have high blood pressure and reported that they didn't have high blood pressure. If we're going to try and see if there's an association between that and high cholesterol, then maybe you should also then give me the information for high cholesterol or age or smoking status or whatever. Just give me an idea of what this population looks like in general, and also specifically with a couple of variables that you're going to be working with. Right? So that's an idea. We were looking for descriptive statistics that'll explain the population and the basic type of data that you'll be working with. I'm sorry, go ahead.
From the table of contents, do you want us to kind of pick one of these and go with it?
Well, if you look at the project description, it actually gives you some suggestions, like, in other words, diabetes and fruit consumption. And so you could choose one of those. Yeah, you could choose one of those topics that are suggested there. Or if you email me and say, I'm been working on this other thing, I'm really interested in this other thing, and there's data in the community health survey that I could use. Or saying, you see, there's 190 variables, so it's going to take you a little while to really look through it all. There's data in the community health survey. I'd rather do that rather than the diabetes and the various other ones that were suggested. Or you might even have a data set that from another class that you've been working on, maybe a project or something like that. So if you want to use that data, that would be acceptable too. But I just need you to this first deadline is so that I know that you're on the right track, that you're working with a data set that's legitimate, that you'll have some shot at getting some results, and you don't have to print. It doesn't have to be statistically significant. In tonight's video or tonight's video lecture video, Levi mentions the fact that it's always nice to prove something is statistically significant, because that encourages people to publish it. So there's a certain publishing bias. In other words, when people do research, if they don't find a statistical significance, that tends to go into somebody's drawer somewhere, or the circular file right in the corner. It gets dumped, right? Because nobody's interested in publishing that, right? But if you can see something that's statistically significant, then it gets published. And since we know up to 5% of the time, we could inaccurately determine something. We could reject the null hypothesis inadvertently 5% of the time if we set that level of tolerance for error. We set alpha at 5%. We know that comes up. So what happens is that a lot of times you might get stuff published more often than needs. That you might see studies more often than you really should that are really shouldn't have been published, because studies that refute it, that didn't show statistical significance, went in the pail, and the only one was the odd one out of all the 20 or 30 people that did the same study is the one that shows up in the journal because it looks statistically significant. So when you listen to the video, you'll get a lot. Not only learn a little bit about the statistics and hypothesis testing and so on and so forth, but you get a little bit of, like, Levi's view and experience with real world publishing and stuff like that of this data. Okay, it's okay. Actually, it's going to be one of the upsides of doing this is it helps me control the data a little bit, so people don't wind up doing. So I don't have to worry about with 25 students of like, somebody will go under the radar and they'll wind up doing a study on two things that are really not associated, and really shouldn't have picked out, so I can control things a little bit better and keep an eye on you guys a little bit better, and kind of like just keep you out of trouble a little bit. The downside is that we're going to be so tired of hearing people talk about diabetes by the time we're done. We do the verbal projects that we won't want to see this ever. We won't want to hear anything about it ever again. So yeah, there is an issue that, like, obviously you're required to do your own work. It's not a team project. So the papers and the presentations will all be a little bit different. But you can you can definitely do all your own work. I mean, definitely there will be overlap on many of the topics. Okay, and what we're going to do is, as we do, I'm going to set up by the 11th, by next Wednesday, I'm going to set up a location where people can log on and they can tell us which of the data sets they're going to use, whether they're going to use diabetes, whether they're going to use something else, so that you'll see as you go through this. It's really a wiki, is really it is. But as you post what you plan on with the data you plan on working with, just very briefly, what the variable it's called, you'll be able to see what other people are working on, right? And if you decide, well, everybody's working on this, let me do something different, you might want to consider that. And if you change your mind because so many other people doing the same thing, you can always go back and change to a different topic. But I want you guys to get into it and tell me what it's going to be relatively early, so that if you got to change direction, we have some time. Yeah, yeah.
Put together in like words and
right.
like
Yeah. Well, I'm
going
to be asking you to just give me the descriptive statistics, right? Just that, okay? And what you're thinking of doing. Now, keep in mind, this week we're going to be going over tonight. We're going over t-tests, right? Which is a method for comparing the means of two groups, right? So in other words, if we want to know the mean age of people that reported they had hypertension versus people who didn't have hypertension, well, these two variables, age and hypertension, would be perfect for us. It's a numerical variable, age, right? And we're breaking up or factoring the ages into two groups: people with hypertension, people with hypertension. So that's what we would do. Now, if we had categorical variables like hypertension and exercise or don't exercise. In other words, you ask people, do you exercise more than 30 minutes a week? And they can either say yes or no. Well, we have two categorical variables. We have hypertension, yes or no, and we have exercise, yes or no. So if we want to know if there's an association between exercise and hypertension, now with this data, we can't. It's not really numerical, so we can't use the t-test. We're going to learn next week about another test called chi-square. Okay, kind of intimidating name. So it's really a simple. Once you see how it's done, it's really a simple concept. And something called odds ratio, which a lot of times you'll see in studies. The odds ratio of exposure to this is this, and so on. So we're going to learn about that next week. Now, this is accelerating things a little bit because we don't have a class on Monday because it's 4th of July, right? Enjoy your weekend, by the way. And the weather looks like it's going to be pretty good. So you got the 4th of July on Monday, so we're not going to have a class. Wednesday, we're going to have a class, and I'll review a little bit of this, but we're going to look at chi-square a little bit, and we'll take the next step on the project. But don't get lost on the project yet. Don't get buried too much in the project, because the following Monday we have an exam. Got to be in class. Got to have an exam. The exam will cover the confidence intervals, standard error, central limit theorem, the t-test, the stuff we're doing tonight. It'll cover just a little tiny touch of what we're doing on Wednesday, which is going to be that chi-square and odds ratio, because I know you're going to need that for analyzing this data. If you look at the schedule, that little picture file with the schedule, I think it shows chi-square going after the exam. I'm moving it before the exam because I want you to practice it. I want you to have tiny little bit of experience with it, because it'll help you understand where you're going with your project, because so much of this data is categorical and not numerical, right? Categorical data, two categorical variables, you check if they're associated, using chi-square and odds ratio, right? So you're going to learn another way to analyze this data. Tonight, we're sticking with numerical data still. Okay, so that's where we stand with this. Now, if I can, without too much trouble, and get it coded correctly, I'm going to post the 2013 data so you can use that instead, right? So, but I think it's almost all the same questions anyway. In fact, they tend to use the same questions because they want to be able to follow the trends that occur over the years in the population of people living in New York City. So for instance, let's take a look right now. And let me go back to our announcements here. I think it's in there. Oh, no, I'm sorry. I should have stayed where I was. Okay, it's here. Okay. Oh, no, it was in announcements. Okay, I'm going to go back here. And in addition to the location for the community health survey data, there's also a site on New York City health data that links to something called EpiQuery. And if I click in there, this is what I see. Whoops. Let me get rid of this. Okay, no, I don't want to do that. Let me go back here. Let me try this again. Oh, I was there, as a matter of fact. Okay, here we are. If I click into EpiQuery, it brings me here. So if I go here, let me see if I have it here. New York City Community Health Survey, 2002 to 2014. I'm going to click in there. It's going to bring me to a page where it summarizes many of the variables that we're looking at when we looked at the community health survey. So for instance, if I'm interested in high blood pressure ever, that's just the variable that we actually looked at. Have you ever been told you have high blood pressure? I can click on that and I can ask it to tell me, to go ahead and tell me, give me back that data for this most recent year, 2014. They actually have this for 2014. Okay, so I'm going to click submit. Now notice there's two things here: age-adjusted estimate and unadjusted estimate. The unadjusted is the actual count. Age-adjusted, we're going to talk about as we get later on in the semester. So for our purposes, I'm going to suggest that for the time being, we stick with the unadjusted or the crude numbers here, the actual numbers that they got back from the survey. But we're going to talk about data adjustment later on. Okay, so I'm going to click submit, and here it comes up and it tells me that 27.4% in 2014 were reported at high blood pressure. That's lower than the percentage in 2011. So this is a function. This is the data is organized so you can see if there's a trend or not. And 72% said they didn't have. Now this is actually extrapolated based on the number of people in the survey to the number of people 18 to 98 in New York City, right? So that's why they didn't actually ask 1.7 million people or 4.6 million people. The survey question, they just figure, oh, with 27% of the total population the total population is that number, but it's really 27.4%. Now, if I wanted to evaluate that from the perspective of various other variables, employment status, so on and so forth, I can factor it within here by that other variable. Like for instance, let's see if there's a difference in gender as far as this is concerned. So I can click submit, and let's see if how it looks if I look at high blood pressure based on gender. And it looks like that it looks like it's pretty close. It doesn't look like a big difference in terms of who was what people were, the percentage of people that were reporting that doctor told them that they were high blood pressure. Now, before this, would you have guessed that more men or more women in New York City have high blood pressure? Men. So why is it that a higher percentage of women are reporting that they have high blood pressure than men? What else is high blood pressure associated with? Yeah, what else? What's the most common cause of high blood pressure? Age. As you get older, your blood pressure goes up, right? So remember we talked about age adjustment? What's happening here is Who lives longer in New York City, men or women? Women. So if you looked at the population of men and women in New York City, there's more older women than there are older men. So the reason why the percentage of women reporting to have high blood pressure is higher than men is not because your initial judgment that men are more likely to have high blood pressure, it's because there's more older women. So in order to take away that age bias, we have to adjust this data. As we get towards the end of the semester, I'm going to sneak in maybe a half hour or so on age adjustment so that we can understand how how you can adjust out a confounding variable like age when you want to really examine, compare two like populations with regard to, say, blood pressure or diabetes and so on and so forth. So that's really pretty interesting stuff. We're going to take a look at that, as I said, later on. Okay, are you guys online? You're okay with this stuff? You get an idea of what we're looking at here when we look at this community health survey. I'm hoping that we're okay with that. Okay, good. Is it okay? Is it okay? Okay, I think we covered that. Okay. Okay, so I'm going to move on to t-tests. And last week, Monday, oh, yeah, things are really tight in the summertime here. It was last week was only 2 days ago. They're short weeks. So last time we got together, we extended our use of confidence intervals into the idea of t-tests. We started with a single sample t-test. And I'm going to open up a data file that's on here rather than go right to like the exercises and stuff. And I have a data file here called single sample t-test. I'm going to open it up in Excel. So here is a population, excuse me, not a population, but a sample of, let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 people, right? Random sample of 9 people. And you guys might remember that the way we calculated a confidence interval for the mean for these 9 people were selected from a population. And we're interested in what's the mean, mu, what's the mean mu for this population, okay? And in order to calculate that, we took a sample of 9 people randomly from the population. As it turns out, the mean for these 9 people is equal to 10. I'll just show you that I did that. Average is equal to the values 2 through 10, right? So, and the standard deviation, now the other thing I'm interested in is the standard deviation of the population, which is sigma. Now, I don't know the population, so the only way for me to get the standard deviation is to calculate it for my sample and say, well, the mean is an estimate of the mean of the samples is an estimate of the population. The mean of the standard deviation of the sample is an estimate of the standard deviation of the population. So that's how I got that. And you can see that that's also showing up there. Standard deviation of those 9 numbers. Okay, so now I say to myself, I think the mean of this population is around 10, but I want another way to describe this. I want a confidence interval. I don't want to say that I think it's around 10. I want to be able to say with some idea of how likely it is I'm wrong or right. I want to have an idea of how to describe what the mean of this population is, because I'm really interested. I'm not that interested in the sample mean. It's only a tool, the sample mean. I'm really interested in mu. That's really what I'm interested in understanding for the population. So in order to calculate a confidence interval, I got to calculate a standard error. And how do we calculate standard error? Well, standard error is equal to sigma. That's equal to sigma, population mean, divided by the square root of the sample size. Right? Well, we don't know sigma, so we're going to have to use the sample standard deviation, right? Which is, okay, which is equal to the standard deviation, my estimate of sigma, over the square root of 9, right? There's 9 people in this survey. Sample size is 9, and that comes out to be 0.91. Okay, that's my sigma. Okay, so now I want to calculate my confidence interval. How do I calculate my confidence interval? Well, it's equal to x bar, right? the mean of my sample, plus or minus both my z-score, right? Which is if I have a large sample, if I know the population standard deviation, that's going to be for a 95% confidence interval, it's going to be 1.96, as we recall, right? My z-score times my standard error. Okay, now the only problem here is, do I have a large sample? No, I have a small sample. Just informationally, a lot of people consider anything over, say, 50 a large sample. And if you have a large sample, you can, and you're not worried too much about immediate precision on this first calculation you're doing. Instead of using, you can actually go ahead and use 1.96, the z value for 95% confidence interval, right? But since we have a small sample, we actually have to use the t-score that's appropriate for this sample size. Okay, so let's look up what the t-score has to be for this sample size. Okay, and I think under our references on Blackboard, I uploaded a bunch. Here's the t-table. Okay, and if I open the t-table, it tells me that for a sample size of 9, how many degrees is a sample size of 9? 8 degrees of freedom, right? For a sample size of 9 or 8 degrees of freedom, the t-score is equal to 2.306. I'm going to use 2.3 for our purposes, right? So if I go back here and I actually calculate my confidence interval, it's going to be equal to x bar, which is 10, minus 2.30, whatever it was, 2.3, times my standard error, which is 0.91. Okay, and let's see what that gives me. I'm going to put parentheses around here just to make sure it does them in the right order. And it's 7.9. Now, the upper limit of my confidence interval is going to be equal to x bar, 10, plus 2.3 times the standard error. I think I can do it. I'm going to multiply first. It's going to the order of operations Excel does is power or root, and then next it does multiply or divide, and then next it does add, subtract. So this should work out right if I just hit enter, and as it happens, it does. So I'm 95% certain, my 95% confidence interval, right? I'm 95% certain the true mean for the population this sample was taken from is between 7.9 and 12. Now let's say that I told you that this was a value for American men. And I went overseas and I asked a researcher in France, have you done a study like this? Oh, well, that information, we did an immense study. We sampled 50,000 men, and we are absolutely confident that the mean for French men is 6.3, right? That's not just the sample mean. They're saying that that's mu. That's the population mean for French men. Well, now, can I say that the average number for the population of American men, mu for American men, is different than it is for French men? Well, with 95% certainty, it seems like I can, doesn't it? Because if French men are between 7.9 and 12 with 95% certainty, American men, and French men are 6.3, we know what French men are, then I'm pretty much 95% sure that French men's average is different than Americans' men's average, right? It's going to be lower or at least different. So really, there's reasons why we don't use the confidence interval this way. We actually use a version of it, which is called a t-test, as we discussed last week. Okay, and the way that we do that is what we do is we calculate a t-value. In other words, we say to ourselves, well, here's the mean for French men. Here's the mean. The mean for American men we think is 10, but there's a certain amount of variability here. And the variability is based on the standard deviation and the standard error. So instead of comparing a confidence interval to a value, we do a one sample t-test. The t-test, the value of t, which is really the number of standard deviations apart the two means are, the value of the sample mean, x bar minus the value of the known mean, mu, which is 6.3, divided by the standard error, the number of standard errors of parts these two are. So what is t equal to? T is equal to 6.3 minus the sample mean, 10. I'm sorry, should have been the other way around. Doesn't really matter, but just so that we keep it straight. 10 minus the known mean, mu, which is 6.3, divided by the standard error of 0.91. So now this time I do have to put these in parentheses because otherwise it'll just divide the value in E8, the standard error, rather than the difference that was really in the top there. Okay, so now I'm going to hit enter, and my t-score is 4.05, right? It's 4 standard errors apart, these two. So now if I go back to my t-table, I can see for a sample this size, my critical value of t is 2.3. What does that tell us? That tells us that if the value of t, the number of standard errors apart, that these two values are, you're not outside of the confidence interval with the number you're comparing it to. You're inside. It's inside the confidence interval. So you really can't say with 95% certainty it's different. But if you're bigger than this t value, then you can say, this t value says that the population that's represented by 6.3 and the population that's represented by a mean from my sample size of 10, I'm not more than 95% sure that I can say that they're different. Reject the null hypothesis, in other words. Okay, we're doing the same thing we kind of did with the confidence interval, except we're using a version of the t-test to do that. And what do we call that value of t that we have to exceed to reject the null hypothesis? The 2.3 that we have here. And you remember what that was called? It's really important number. It's really an important number because that's the number that we know for that sample size that we have to exceed when we calculate the t-score to reject the null hypothesis. Really important, urgent. Think ICU. Critical. It's the critical value for t, right? The critical value. Anybody else? Anything? Okay, good. I got at least one person got critical. Good. Yes. Well, alpha is the level of error we're willing to accept. That's the 5%. In other words, 95% confidence interval. That means we'll accept up to 5% chance of being wrong. If we had said 99%, if we had said we only accept 1% chance of being wrong, that's half a percent in a lower tail, half percent in the upper tail. 90% confidence interval for the same sample size, our critical value would have been 3.55. We want to be 99% confident, or we want to lower our chance of being wrong. It's a wider confidence interval, and it's also a higher t-value. But in fact, we're better than 99% sure because we actually exceeded both of those values. Okay, so let me do this in SPSS. Now, you guys, if you're at home or you're here, open up the same data file. I gave you a version of it that was in SPSS, right? A SPSS file. Let's see if it'll open it for me. Single sample test. Let's see if we get the same answer. I may have to tell you on my version, I think I have to open it from here. Open? It's on Blackboard under the date, under session 8, data.
There is no session yet.
Don't tell me that. There's no session 8. There's no session. How could that be? Hang on a second. You got to tell me this stuff. Jeez. Hang on a second. I can't believe this. Is it possible that like it got turned off somehow? Because I know I turned it on. Sometimes Blackboard drives me crazy. Okay, let me go in here and find out about this. Okay, class sessions. Okay, not available. Nope, that's this. Yeah, it also says not. There's a function in there where you can get it to turn on by itself at a certain time, but it never works. So I got to give up on that. Okay, it should be available to everybody now. Let me click in there. Yeah, if you click in there, you'll see that there's date. There's date. Let me see. Oh, I don't see the. Yeah, if you click in there, lab session 8. If you click into the next folder, lab session 8. In that folder, you'll have the data files. Yeah, single sample SAV for the and so on. I have it on my desktop already. You can like save it, add it there onto your desktop. So I'm going to say, okay, let me see if I've already opened it. I already have it open. And you'll notice that the same values that we had before are now in SPSS in the first column, right? So now how do I do a t-test in SPSS? What am I doing when I do a t-test? I'm comparing the means of two populations when I do a t-test. So if I go to Analyze and I go down to Compare Means, that's what I'm doing, right? So that's where it's hidden. Compare means, and this is a one sample t-test. Why one sample? Because we only sampled one population. The other population, we knew what the mean was, right? So I'm going to click on one sample t-test. And in this case, it's easy to see. I got a problem here. What's the problem I have here? It thinks it's a nominal variable. So I gotta go back out of here. I gotta go to variable view, and I have to go, see, there it is in variable view. And under here, under measure, I'm going to change that from nominal to scalar or numeric scalar. I go to from data view, I go to variable view, and then under variable view, this is what was there, nominal. If you look behind me, you'll see that it said nominal there, right? I click in there and I change it from nominal to scalar. Okay, so because it saw all of those. I made this problem simple by using all integers, small integers. So it thought it might have been a nominal variable. Okay, that was the guess that SPSS used. Okay, so here are all the values. Now I'm going to go to Analyze, Compare Means, one sample t-test, and I'm going to take the x variable and move it in because it's my test variable. That's the number I'm going to find the mean of. Now, what am I going to compare it to? I'm going to compare it to the value for that other population, which I said was 6.3. Okay? So now, I don't think there's anything on options I really need. Confidence interval percentage, 95%. This is the point. This is a place where if our alpha was 1%, our acceptable level of error was 1%, we would change that to 99%. Let me go ahead and do that. I'm going to do it for alpha is equal to 0.01, just to change things up a little bit. So I'm going to change that to 99%. I'm going to click continue. So now it's going to compare the mean for the test variable x to the known mean 6.3 to see if there are enough standard errors apart to reject the null hypothesis. So I'm going to click OK, and our output window is going to come up, and it's going to tell me we had 9 in our sample. There were 9 values. The mean was 10. Standard deviation was 2.7. The standard error was 0.913. That's the same thing we got in Excel, right? But now let's look at the t-test. The value of t is equal to 4.053. Well, we know that we would reject the null hypothesis with that value because we know from a table that the critical value for an alpha of 1% is 3 point something, 3.3, I think it was. And this is more than 3.3. But SPSS actually calculates out for us 8 degrees of freedom, the significance, the probability of getting that big a t-value if you're wrong about rejecting the null hypothesis is 0.004, which is 0.4%. So why, the significance, same thing that's being called a p-value, probability of being wrong, p. So what did I say my alpha was? My alpha was 1%. Is 0.004 less than 1%? 1% is 0.01, right? 0.004 is smaller than 0.01, so I can reject the null hypothesis. So when I do the t-test here, I don't go to the table. I don't look up the critical value. It tells me what my actual probability is, right? So of being wrong is 0.004. And as long as it's below my alpha value, my acceptable level of error, then I can reject the null hypothesis. My p-value has to be less than the alpha, or my critical value has to be more than what the calculated value is. T has to be greater than the critical value, or my p-value has to be less than alpha. And they go along together. The bigger the t-value is, the smaller the p-value is. Okay, so now I'm going to move on to the next possibility. Next possibility is a situation where I don't know what the mean of the other population is. So now I have, instead of a one sample t-test where it's one sample I take, now I have to sample two populations, and now I have two means that I really don't know the population mean for. Okay, so I'm going to go into Excel, and I'm going to open up the other piece of data I have is two sample t-tests. I'm going to open it up in Excel. Okay, and here we go, and I'm going to blow it up a little bit so we can see it a little bit better. And I'm going to close this up. Okay, and here is where, I made up bogus variables. Here is a set of variables where I'm comparing a sample of men to a sample of women, right? So how would I calculate the t-score for these two Well, first thing I need to know what the means are, right? So I need to know what x bar is for both of these samples, right? The mean. So the mean of this is equal to average, parentheses, and the average for men is equal to 10. Same numbers we used before. Average for females is equal to, 7.5. Now, is there any guarantee that the mean for the population of women is different from the mean for the population of men? It looks like it's different here, right? But is that a guarantee? No, it's not, because this is just a sample. We have no idea yet how likely it is that the difference that we just got here was just a sampling error, just by chance that we got a lower number for females than males, or if we got a lower number for the average in this sample for females because there really is a difference in the two populations. We don't know yet, right? And we won't say that we know unless we can reject our null hypothesis. So what are our hypotheses here? What's H null, right? Okay, what is H null? H null is that the mean mu for males is equal to mu for females, right? Mu for females. And what is our alternative hypothesis? That they're not equal. Okay, we could, moving forward, when we get better at this, we can talk about one-sided, but for now, we're just going to stick with two-sided. Does not equal the mean for females. Okay, so now, how do I calculate this now? Well, now I have to compare the two of these. I have to calculate a t-value. So my t-value is going to be, I don't know the mean of either one of them, so it's going to be equal to x bar for males, minus x bar for females over the standard error. We didn't calculate the standard error yet, did we? Right? We have to calculate that, don't we? I'm gonna take that. See what it'll let me. Okay. So now I have to actually calculate that standard error. Okay, so now I'm going to go over here, and standard error is based on the sample size and the standard deviation. So I'm going to calculate it based on my sample. So my x bar is that. My standard deviation is equal to, well, for the males, is equal to that. For the females, it's equal to that. Okay? Now, which one of these two should I use? I can only use one standard error, right? Which one should I use? There's the rub. We have a problem here. We have two samples. We have two different standard deviations for the two of them. So now the standard error for this one would, if we just calculate it from that one, it would be this number over the square root of 9, which is 3. It would be this. And the standard error here would be equal to this number divided by the square root of 9, which is 3. Okay, so we have two different standard errors here. So what do we do about this? Okay, so what we're going to do now we suddenly have a situation where we have two different possible outcomes for two different directions that we can go with regard to the standard error in these two samples. One thing we could do is we could assume that the two standard errors are the same, right, and use something in between. The other possibility is that we could say that they're different, and then we'd have to make up some sort of way to estimate what we think we should be using. Okay, so or maybe in one situation we could combine the whole things, and or in this situation we could just go somewhere in the middle or something. So we have to decide, what are we going to do? We have two possibilities here. One possibility is equal variances, equal standard error. In other words, another way of saying equal variance in the two populations, or unequal variance. Okay, so one of the simple ways that we have to look at this, there's tests that we can do, statistical tests to tell us whether we should assume equal variances or unequal variances. We could actually do a statistical test for it. However, a shortcut to that is to simply examine the data, the standard deviation, and the standard errors, and for our purposes, we could say that if one is not twice what the other is, we're going to assume that the variances are equal. Okay? Just as a general rule. Is that the best way to do this? No. But I mean, if we want to get something done here tonight, that's the way we're going to have to probably look at this. If it's more than twice as, if it's more than one is more than double the other, then maybe we'll say to ourselves unequal variance. If it isn't, maybe we'll say, for our purposes for this analysis, we'll say that they're equal variances. So in this case, what do you think? Equal variances? I think so, right? Okay, they're pretty close, the two variances. Two standard errors, two standard deviations, pretty close. The two standard errors, pretty close. I'd say equal variances, right? At least for our exercise here. Okay, so now that means that, maybe that means I can combine all the data and calculate one standard error. Doesn't that sound like a good idea? That way we have, when we calculate our means, we only have 9 people. But when we calculate our standard error, we're looking at 18 people. We have a better measure than we do if we don't combine them, right? So this helps us out a little bit. Okay, so now, if you go back into Blackboard, you will find a couple of files. Let me get this stuff out of the way. I need like a 27-inch screen here or something to help me out with this stuff, because it's just this little screen here gets so crowded. Okay, so now I have to go. Here I am. Okay, I'm going to go back here. And on Blackboard, you notice that I gave you a bunch of, it's got references under the lab exercise. I gave you a bunch of different things. For instance, I gave you, among other things, this thing called t-test procedures and variations. And if you open that up, it tells you, okay, compare the means of two populations using hypothesis. That t-test, standard deviations assumed to be equal. That's our situation right now. We decided we assume them to be equal. Well, in that case, what you want to do is you're gonna calculate a pooled standard deviation. How do you calculate a pooled standard deviation? It's basically kind of like a weighted average. Okay, so your pooled standard deviation is going to be sample size 1, which is 9, minus 1 is 8, times the standard deviation of sample 1 squared, plus sample 2 minus, which is 8, times the standard deviation of the second group squared, which is 8 times the standard deviation squared, divided by n1 plus n2 minus 2, which is 18 minus 2, which is 16. So we can calculate that. And we're going to use that pooled standard deviation in our formula for t, which is x1 minus x bar 1 minus x bar 2, divided by the pooled standard deviation times the square root. Well, instead of square root of the, the sample sizes could have been different. Instead of that, it's going to be 1 over 9 plus 1 over 9, 2 over 9. Square root of that times the pooled standard deviation. A little bit more tedious, right? But that's how we're going to. Well, what would have happened? What would have happened? And then for the degrees of freedom, we would use n1 plus n2 minus 2. Just 9 and 9 because we were combining them. So it makes kind of sense, right? We're going to subtract 1 from each and then combine the rest. Okay, what about if we had decided they were unequal? Well, if they were unequal, you go to the second page here, and here's the formulas you would use for unequal variance, but unequal. And for unequal, you would say t is equal to x bar 1 minus x bar 2 divided by the square root of the standard deviation of group 1 squared over the sample size 1 squared, that's 9, plus standard deviation of sample 2 divided by sample size of 2 happens in this case to be the same, 9. Add those together, take the square root of the whole thing, and divide that into the difference between the two means. And that would give you your t-score. However, in order to decide what critical value to use, you need to know your degrees of freedom. When we used equal variances, the degrees of freedom was just the sum of the two sample sizes minus 2. But with this, calculating the t-score is look at that. Is that ugly formula? Let me tell you a dirty little secret about the formula. Nobody actually solves that formula. What most people do is they say, let's just take the smaller of the two groups and subtract 1 from it and call that the degrees of freedom. So in this case, we would use 8 as the degrees of freedom. Otherwise, we'd be here. We don't want to do that. It's nasty, right? Okay, so this is how you would calculate a t-score for equal variances assumed, for unequal variances assumed, right? So there's two directions we can go with this. So I'm going to actually calculate this for now. Why am I thinking to myself, I'm going to calculate this using a calculator or Excel? But boy, man, is that a waste of time? Why is it a waste of time? Guess what's going to do this for us? Yeah, but what's going to do this for us like in an instant? SPSS. Okay, so why not just do this in SPSS? Well, the reason why we're not going to do this in SPSS is because you need to learn this stuff, right? Not just sticking to SPSS. So you understand this process. You understand, so you just don't do stuff in SPSS without understanding what you're doing, because you can really go kind of, really off the deep end. When you have a powerful tool like that, you really don't understand the calculations that it's doing. So, okay, I'm going to do it for this version. So let me go back to Excel. Okay, and you guys do this with me. Don't leave me doing this alone. Okay, do it with me. Okay, so what am I going to do here? Now, what I'm going to do here is I'm going to say, let me move this out of the way. Let me move this so I can see what I'm doing here. First, I'm going to calculate my SP, my pooled standard deviation. SP. My pooled standard deviation is going to be equal to, and you know what I'm going to do? I'm going to calculate this in steps. First, I'm going to do n minus 1 is 8 for this first sample. 8 times the standard deviation times the standard deviation for group 1 for the first group squared. That is the standard deviation is 2.58 times 2.58 times itself squared, right? And that is the first part of the top of that, the first part of that numerator. Now, the second part of that numerator is going to be equal to 8, which is the
it's 7 o'clock.
Excuse me, I should have said n 8 is n minus 1 for that second group, times standard deviation 2 squared, just multiplied by itself. Probably easiest way to do that. Right? And now I'm going to add those two together. It's equal to the sum of these two values, okay, which is 83. So that's the top part of that equation. Now the bottom part of that equation is going to be equal to 9 plus 9 minus 2. It's going to be equal to 16, right? And what do I have to do with this whole thing? I have to take the square root of the numerator divided by the denominator. So I got to broke it into a few steps to make it easier. So my standard error is equal to 2.28. And if you look, it's kind of in between those two, isn't it? It's really a weighted average, right? So that's my standard error. So now when I calculate my t-score, how do I calculate my t-score? My t-score is going to be equal to x bar 1 minus x bar 2 over the standard error. Actually, really should be parentheses in front of those two things, so you don't miss it. So what is t equal to? T is equal to let's see, x bar 1 was 10 minus 7.55 divided by this pooled, oh, I'm sorry, I got that wrong, didn't I? Now it's got to be over, look at this, got to be over this funky equation over here, okay, which is going to be equal to, okay, so now let me see if I can't do that in one step. Okay, you could actually do it in a few steps. I'm going to try and do it in one step. It's going to be the first mean minus the second mean, right? Over the square root of the pooled standard deviation. The pooled standard deviation is this number right here. I'm sorry, I got that wrong. That's pooled standard deviation. I'm sorry, that's not standard error. Oops, that's not standard error. That's standard deviation. So I just want to make sure that we have that SP, right? Because we're really kind of calculating the pooled standard error here. Is equal to x bar 1 minus x bar 2. Okay, right? Because we're actually calculating the standard error on the bottom, divided by the pooled standard deviation, which was 2.28, right? Times the square root of 1 over 9 plus 1 over 9. Okay, let me bring this over. Okay, so now let me see what this is going to do. It's going to add these two together before it's going to do this operation, 1 over 9 first, 1 over 9 first. Then it's going to add them together. Then it's going to multiply it by the bottom. What I need to do is put a parentheses around these two also. Okay, I'm gonna roll the dice here and hit enter. Anybody have any opinions there whether this is going to work or not? Okay. No comments from the peanut gallery, so you can hit enter. And the t value comes out to be 2.269. So now, does that exceed the critical value that I need to reject the null hypothesis? We don't know yet, do we? We got to look up what the critical value is. What do we need to know to look up what the critical value is? We need to know alpha, which is 5%, 99% certainty. Alpha is 5%, 95% certainty. And the other thing we need to know is we need the degrees of freedom, right? Degrees of freedom. What's the degrees of freedom for this kind of calculation where we know where we're saying that they're equal variances? It's the two samples added, two sample sizes added together minus 2, which is 18 minus 2 is 16. So this is 16 degrees of freedom. So if I go to the t table, okay, where is it? Here it is. If I go to the t table for 16 degrees of freedom, what's my critical value of t? 2.12, right? Let's go back here. 2.12, my critical value, t critical, is 2.12. Can I reject my null hypothesis? Is my t-score greater than my critical value? Yes, that means the p-value is less than 0.05, which means it's less than alpha, so I can reject my null hypothesis and accept my alternative hypothesis, that there is a difference between the mean for males and the means for females. Okay, I'm going to do exactly the same thing now, just like we did before, except in SPSS. Okay, how are you guys doing online? Are you guys getting this? Does it make sense to you so far? I know it's tedious, but you have this chart which gives you the formulas and stuff like that. And if you're careful, you can navigate your way through them. You don't necessarily do what I did when I calculated the standard error there, the denominator of that fraction, and just try and do it all in one box in Excel. You could do it stepwise. You could use a calculator, so you don't need to like dive into it like that. So are you guys okay with that? Are you following this online? I need to get some feedback from you guys. Yes. Okay. Yeah, the people that are following it saying yes. The other people are like rolling their eyes at me now, right? I think I can kind of feel it. Okay. So let's look at SPSS. Let's say I asked you to do this using Excel or your calculator and the right formula on SPSS. Okay, good. You go back over later. Great. Okay, let's say that I asked you to do it in Excel, and I asked you to show me your work in Excel or something like that. I probably usually will leave you to your own devices. But let's say I ask you to calculate it manually, and you say to yourself, I just did this, but I'm not too comfortable with the answer. Maybe I should check myself. What's a good way to check yourself? Well, a good way to check yourself is to put the data into SPSS and see if you get the same result. So I'm going to go over to SPSS. Okay, we'll examine how this works in SPSS. And I'm going to open that data file. Open, data, and I'm going to navigate back to where I was before, which is, let's see, well, no, that's there. I need where is it? I need, what is it called? I think it's session 8, and it's inside data files. Yeah, single sample, 2 sample. There it is, right there. I think I must have put it in there twice. Okay, let's see if I got the right one. Yeah, that looks right. Notice how the data is formatted in SPSS differently. Male and female is one. Actually, if I just turn off the value labels, you can see male and female is 1 and 2, right? So this is the way we separate that. This variable is the whatever that number is, weight, height, BMI, whatever, and this variable is a categorical variable that we're going to factor that the averages into. Okay, male and female in this case. So I'm going to go to Analyze. I'm going to go to Compare Means. I'm still comparing means. This time, there are 2 independent samples. We took a sample of males, the male population. We took a sample of the female population. Each of them were independent samples. Each of them were random samples. So I'm going to go and it's going to skip one sample t-test because there's 2 samples involved and go to independent samples t-test. Notice at this stage, SPSS doesn't ask you to make a judgment. Should I use equal variances or unequal variances? Doesn't ask. Okay, so I'm just going to click on that, and it's going to open up and say, okay, here's the test variable. I'm going to put this in here anyway just to see if it'll work. It thinks the x variable is a nominal variable for the same reason as before, because it's relatively low in integers. But I'm going to factor the means for that into the 2 genders. Now, SPSS requires you to tell it what the values are for the categorical variable. So you got to tell it that group 1 is a 1 and group 2 is a 2. I think that's right. I would have to look in the coding and in the variable view to check that. I think 1 is female, 2 is male, but I could be wrong. It could be 0, 1. If that's the case, it won't work right. Options, I can tell it's 95%. What's that? 1 is male and 2 is female? Or 0 is female? I think it was 1 and 2. The 1 and 2s. Oh yeah, look, there's 1 and 2s there. So it doesn't really matter at this stage which one's which. So since we want to be 95% certain and alpha acceptable level of error alpha of 5%, I'm going to leave that at 95%. And then I'm going to click OK. Okay, and SPSS did the analysis. And what did it do? Well, it gave me the mean, standard deviation, and standard error for each of these 2 groups. And look, it's basically the same as when we did it manually. There's something wrong here because the standard error came out different when I did it in Excel. And I think it's possibly because one of those numbers, I think when some previous time when I was playing around with it, I might have tickled one of those numbers just for the hell of it. But at any rate, we were doing the right thing when we did this, right? So that's the result we got for the so on and so forth. Now SPSS then gives us the results for the t-test. It still hasn't asked us whether we want to use equal variances or not. But look at this. If I look at this box that we have here, the output that we have, look, there's one line on top that says equal variance is assumed and gives us a bunch of results. And there's another box on the bottom that says equal variance is not assumed. Well, you know what it does? It calculates it both ways, the t-score both ways. So now we have to decide whether to use the top line for our result or the bottom line for our result. Okay, so let's take a close look at this. The first part I see here is this 4-box set right here. F, significance, that's what's set p-value, and a number, and so on and so forth. I see this thing here. It's called Levine's test for the equality of variances. This is actually a test that SPSS is doing to decide whether you should use equal variances or unequal variances. Okay, and the way this test works is it's just like any other hypothesis. The null hypothesis is that things are equal. So what would you say the null hypothesis is? Equal variances assumed or unequal variances? What's the null hypothesis, would you say? Equal variance is assumed, right? They're equal. The variances are equal. That's your null hypothesis. So that means that I'm going to stick with the top line unless SPSS gives me enough information to reject that and say they're not equal and use the bottom line. Okay? So what do I need to reject that top line equal? Well, I need a significance or p-value less than 5%. Is the significance for this test of equalities, is it less than 5%? It's not less than 5%. It's 24%. Remember, that's a proportion. 0.24, right? It's 0.245. We need it to be less than 0.05. The significance right here. No, we're looking at the 4 boxes right here. Look up. We're looking at the 4. This is our test for whether or not the significance, whether or not the standard errors are equal. Look over my shoulder here so you can see what I'm circling. This is the part where we're trying to decide whether or not we should use the top line or the bottom line. Once we see that this is greater than 0.05, we stay with the top line. If this is smaller than 0.05, we reject the null hypothesis that they're equal, the variances, and use the bottom line that they're unequal. Okay? So this tells us, let's stick with the top line. So what's the t-score that we get? The t-score is 2.184, approximately same as we calculated, right? What are the degrees of freedom? 16. That's what we calculated, right? And what is the significance? What's the probability of being wrong if we reject the null hypothesis? In other words, the p-value. What is it? It's 0.044. What's our alpha error? What's our acceptable level of error? 0.05. Is our probability of being wrong less than 0.05? It is. So we reject the null hypothesis. Okay? That's simple, right? Okay, so you can reject the null hypothesis here. Now, it does some other calculations here, including a confidence interval for the differences between in other words, this is actually the difference between the mean, confidence interval for the difference between the means, x bar 1 minus mu1 minus mu2, of the two populations. Don't worry about that for now. You guys that want to view this a little bit more advanced will notice that the 95% confidence interval for the difference between the two means is 0.07 to 4.8. So between 0.07, if there's no difference between the means, what would you expect the difference to be? 0, right? So we're 95% sure that the true difference between the two means is between 0.07 and 4.8. In other words, 0 is not in there. So we can say that the differences between the two means is not 0, so they must be different, right? We reject the null hypothesis that they're the same. But you guys can stick with the t-test if you want and the significant two-tailed significance, or you can do it the other way around. And you'll notice that you get a different result if you use the unequal. For the most part, unless it's really unusual samples, you're going to get basically usually the same result or very close to the same result, whether you use equal variances or unequal variances. unless the difference in the standard deviation is enormous between the two groups. Okay? So now, with SPSS, we didn't have to use the second set of equations. With SPSS, we could just do it with, tell it to do our analysis using independent samples, and then use SPSS to decide whether they're equal variances or unequal variances. Now, there's one other test on this that I want to show you while we're at it. Okay? And the other quirk on this, if you look at the data files, okay, I'm going to go into data files again. If you look at the data files, one example that I gave you was paired samples t-test. I'm going to double click into that. Okay, and I'm going to open it up, and there we go. There's a paired sample t-test. Okay, so in this example with paired samples t-tests, let's take a look at what happened here. What happened here is that this is not two groups of people. This is two drugs, same people. In other words, this person in row 2 over here, they took a placebo for 2 weeks, and then they took the drug for 2 weeks. When they took the placebo, their blood level for whatever enzyme was 6. When they took the drug for 2 weeks, it did the same. They didn't get any change, right? When this person did it, their level went from 8 for the placebo to 4 with the drug. So the drug lowered their the value for them. So what's happening here is this is not males and females. This is subject number 2, subject number 3, subject number 4. These are people that the data represents with the drug and without the drug. What, like for a period of time, let's say, what their measurement happened to be. So I could go over here and calculate the difference that it made for each patient. So that's going to be equal to this value, the placebo minus the drug, right? Hit enter. And then I'm going to copy this down. Okay? So all of these are the differences between the placebo and the drug for each individual person, right? So now, if the drug was no different than the placebo, what would you expect the average of all these differences to be? No difference between the placebo and the drug. You'd expect all of them to be 0, 1, -1. So you'd expect this average to be 0. The average comes out to be 1.5, which means that the placebo average was higher than the drug average. But really what we're comparing here is not the actual numbers, but the differences, right? So what's my null hypothesis here when we're comparing the drug to the placebo, right? Well, I'm saying that the drug and the placebo have the same number, but I don't want to put it that way. I'm saying what's the difference for each person, right? The difference for the placebo and the drug, right? I'm saying that is equal to, what's it equal to? It's equal to 0. That's my null hypothesis. There's no difference between the placebo and the drug, or the difference between the levels before and after, or whatever, is 0, right? So the difference is equal to 0. And what is my alternative hypothesis? That the difference is not equal to 0. It could be bigger, it could be smaller, but it's not equal to 0. So I have an average difference here, right? So I want to compare that average difference to a certain value to see if it's really different. And what is the value I want to compare it to? 0. When we do paired sample t-tests like this, we're really just calculating the differences and comparing it to a set value of 0. And what is that? That's really a single sample t-test, right? Okay. So I can actually see this is my a single sample t-test. I find the average difference, which is 1.55, right? And my t value, what's my t value going to be equal to? It's going to be t is going to be equal to the difference between these two values divided by the standard error. Now, what's the standard error equal to? Okay, well, let's see what the standard is. Standard error is going to be equal to the standard deviation, equal to the standard deviation, because that's all we have, divided by the square root of the sample size. Right? Okay, so what is my standard error equal to? My standard error is equal to the standard deviation of this group here, of all these differences, right? Divided by the square root of the sample size. The sample size happens to be 9, so that's divided by 3. So the standard error is 0.89, is almost 0.9. So my t-score is going to be equal to the difference between the two of these divided by my standard error. And that comes out to a t-score of 1.72. Okay, that's my t-score, it's 1.72. What are my degrees of freedom? What do you think it is, 18, or you think it's, would you base it on 18, or would you base it on 9? Which one would you choose? 9, what would you choose, 18 or 9? Right, there's 18 numbers, but there's only 9 differences. Well, since the sample that we calculated was really just a 9, our degrees of freedom is equal to n minus 1, or 8, right? Degrees of freedom 8. So what's the critical value for t for a sample of 8 degrees of freedom? Let's find that again. Whoops. Let's see. Was it 2.1 something? 2.1, let's see, 8 is 2.3. Okay, so let's go back here. So my degrees of freedom, okay, so my t-score is 1.72. My critical value of t critical, my critical value of t is 2.3. Can I reject my null hypothesis? My critical value of t is smaller than my value of t I calculated is smaller than the critical value, so I fail to reject the null hypothesis. Do I accept the alternative hypothesis? No, I don't say I accept the alternative. All that's happened here was I failed to reject it. I haven't proved that they're not different. All I've done is fail to prove that they are different. So I fail to reject the null hypothesis. When I do reject the null hypothesis, situations like that, I say I reject the null hypothesis and I accept the alternative. But in the case when you fail to reject the null hypothesis, you make no conclusion about the alternative. You just say, I failed to reject the null hypothesis. Let's do the same thing now in SPSS. Okay, so let's open up SPSS. Okay, and I'm gonna, I think on here I also, if it's not there now, I'll be posting instructions, step-by-step instructions for doing the same thing in SPSS. I'm going to say analyze. I'm going to say compare means, except this time, what kind of samples do we have? Paired samples, right? Okay, there's a problem here though. I don't have that data set open. Do I have that data set open? No, I got 2 samples. I got to say open data, and I got to pull up that data set, paired samples. Here it comes. There we go. This is a paired sample. Placebo, that's patient 1, patient 2, patient 3, patient 4, right? And there's the placebo and the drug, okay? And now I know that the only reason I can do this is because I know that these 2 results were for the same person, right? Okay, this could be before taking a drug, after taking a drug. This could be before a training program, after a training program. It could be before smoking a cigarette, after smoking a cigarette, right? You might, for instance, you might want to check cardiovascular performance in people that smoke, right? And you might ask them to do a certain task before they smoke, and then repeat that task after they smoke, right? And see if there's a difference in their performance, right? But that would be the same person doing the test. So you wouldn't be interested so much in each individual measurement as much as the difference for that person. Now, could you do that with different people? wouldn't make sense with different people, because you wouldn't say, I'm going to take this woman and test her before she smokes, and then I'll take this man and test him after he smokes and compare and subtract one from the other, because you don't know what they started with, right? That wouldn't make any sense. So this only works if you really have paired samples in order to do this, like the same person before and after or under different circumstances. Okay, so I'm going to go up here to Analyze, Compare Means again. That's what we're doing. Paired sample t-tests. I'm going to click on that, and it's going to ask me, okay, which are the pairs that we're going to work with? Well, see, now notice it's going to wait for you to put 2 in. So I'm going to put in the placebo results. I'm going to put in the drug results. And I'll click on Options, and 95%, I'm going to stick with an alpha of 5%. And then I'm going to say, okay. And the output window is going to open up, and let's see how different this is than what we saw before. Okay, placebo. You had 9 people. The average was 10. The drug was 8.4. With the drug, the average was 9. Okay, so on and so forth. It didn't really use that data, though, because what it did was it went down here and it said, oh, okay, let's see. Don't worry about correlation. We're going to get to that. It went down here and it said, paired samples t-tests, paired differences. It looked at the differences, right? Remember we calculated the average difference was 1.55? It got the same thing we did. The standard deviation, it calculated the same way we did, right? It's really basically a single sample, a form of a single sample test. Okay, it calculated the standard error by dividing it by the square root of 9. It calculated the confidence interval for the differences, right? The confidence interval is minus 0.518 to plus 3.69. Oh, that's a problem. Wasn't our null hypothesis that the difference is equal to 0? And our alternative was that difference is not equal to 0, right? The average difference, right? Well, here we can't say the 0 is within this confidence interval. So I can't say it's outside of our confidence interval. So it's possible that 0 could be really the result. And that's why we failed to reject the null hypothesis. If you use the t-test, the t-score, if the calculator is 1.73, just like we did, and it looked up the probability of getting that big a t-test, t-score, how many standard errors apart the two results are, right? 0 and 1.55. How far apart are they in terms of standard errors? And it says they're 1.72. At 8 degrees of freedom, you have a 12.2%, 0.122 chance of error if you reject the null hypothesis. Is that less than 0.05? No. So we fail to reject the null hypothesis. Okay? So I'm not looking too much at these guys online because you don't. I'm sorry, Cheryl. But you mean you want me to repeat this part about the paired sample? Is that what we're talking about? I don't know when the question was asked. Never mind. Okay. All right. So you have what did we look at tonight? We looked at, well, first of all, we looked at the data set that we're going to be working with when we do our projects. And we then looked at an important tool for analyzing numerical data. If you choose to use strictly categorical data or nominal data from the survey, then this is not going to do you any good. You're going to need to use what we work with on Wednesday, which is chi-square and so on and so forth, right? And you got to see that's pretty simple. That's, I think, pretty straightforward stuff. It's not quite as confusing as some of this is, right? But we learned that we can do a t-test to compare the means of two populations. Okay, and we might wind up doing it several different ways. One way is a single sample versus a known value for a mean, for a population. We could do it where there's 2 samples, and in one case with those 2 samples, where the variances are equal, where we assume the variance is equal. The other one is where we assume the variances are not equal. And the third way we could come across this data, if it's the same person measured before and after an intervention. In other words, a paired sample. In other words, we've got a value for them before and a value for them after. So all we're really interested in is whether what the difference is, whether the value went up or down, right? So we could look at that almost like a single sample test, comparing the difference to zero, no difference, right? So now we left out one possible situation where we would be comparing two samples. Anybody think of what that might be? What did I leave out? It's another form of numerical data, except it's binomial data, right? Whoa, when binomial data, that's kind of categorical, isn't it? Yes and no, right? So we have situations where we might be able to use a t-test for categorical data or when we're comparing two populations. Okay, so let's take a look at how that might work. Okay, let me see if I can't find this. Okay, let's do, I have any samples of it here? Proportions. I'll have to make one up. Okay, see if I can't make one up. Okay, let's see. Let me get Excel open. Let me give you a quick example of that. Okay, let's say that I know that I was in Paris about this past October, and everywhere I went, there were butts on the ground. They smoke like chimneys in Paris, right? They have a large population of smokers. Let's say I do a random sample of people in Paris. Oh, and actually, I do a very large sample of people in Paris. I have very good data about smoking in Paris, and I know that 34% of people in Paris smoke. Okay. Now I want to see if it's a different percentage of smokers, different rate of smoking in Paris versus New York. Okay, so I go out. I don't have the money or time to go around and survey all 8.5 million New Yorkers, however many of us there are nowadays. So I do a random sample of 100 people. Right, my sample size is 100. I'll do it this way. N is equal to 100. There's a random sample size of 100. And I find that 28% of New Yorkers are smokers. I'm going to call this P cap, 0.28. 28% are New Yorkers. I'm going to call this P, because P, this is a known proportion for France. Okay, so I'm saying to myself, gee, I sampled those 100 people, and I found that the proportion of smokers was 28%. However, it looks like it's less than the rate of smoking in France. But in France, we actually knew what the population proportion was. In New York, all I know is those 100 people. So I don't know what P is for sure in New York. That's one of the reasons I call it P cap, because it's based on, it's actually a statistic, not a parameter like this one is. So this is a statistic. So I want to compare the two of them. Are these different enough that I can say with 95% certainty that the rate of smoking in France is different than the rate of smoking in New York, right? That's really what I want to find out. So what do I want? What's my null hypothesis here? What's my null hypothesis? What are my point estimates here? Normally my point estimate would be mu1 is equal to mu2, right? The actual population means our point estimates, right? But in this case, we want to know whether P1 is equal to P France, P France is equal to P USA. The proportion of smokers in France is equal to the proportion of smokers in the United States. What's my alternative hypothesis? Let's stick with two-sided for now. That the proportion of smokers in France is what? Does not equal the proportion of smokers in the US. Okay? Okay. So, how do I figure this out? Well, now I'm going to do a t-test, just like I did for proportions. How would a t-test be structured here? Well, a t-test works the same way here. T is equal to the proportion of smokers in France, right? Actually, I'm going to start with USA. Proportion of smokers in the US. I don't really know the proportion of smokers in the USA. So I'm going to put P cap over here. The proportion in my sample, minus P France, right? The difference between the two of them. Now, what I want to know is the difference of the two of these, how many standard errors apart are there? So it's going to be P cap minus P France over the standard error. P cap minus P over the standard error. It's just like doing it for a mean, a single sample for a mean. Well, in a sense, okay, so now I'm going to take a look at how am I going to calculate what my standard error is. Well, I got a sample of 100 people, and it was 28%. There's a couple of ways I could figure this out. And one way is to say to myself, well, what's the likelihood? Remember I wanted to find a confidence interval? What did I use for the standard error in a proportion for the confidence interval? Great. Thank you for remembering that. Square root of P times 1 minus P, right? Divided by N. All of that's underneath the square root sign, right? So we're going to do the same thing here, find a confidence interval. So now, should I find a confidence interval for the 0.28 or for the 0.34 and check to see? I could do this two ways. Find a confidence interval for the 0.28 and see if the 0.34 is outside or inside of the confidence interval. Or I could find a confidence interval for the 0.34, which I know more securely, and see if the value 0.28 is inside of it. You could probably do it either way. However, it seems to me it makes more sense if I use the 0.34. So when I calculate my standard error, I'm going to calculate it. It's equal to the square root of, and I'm going to stretch this out a little bit so I can see it, square root of 0.34 times 1 minus P, which is 0.666, right, over N. Put all of this in parentheses. And my standard error for this for the proportion 0.34. What did I do wrong? Square root. That's right. This number, then this, I should do that first, right? That divided by N. Is there on the top? Don't I need that? I think I need that to make sure it finds the square root of everything now. Nope, see, now there's an error there now. Was it not like, did I type something? Is there an extra space or something? Okay, I'm going to do this. I'm going to do it. I'm not going to fight with this. I'm tired and I'm not paying it. Oh, I'm sorry. Yeah, I didn't put a number in there, did I? That's why it said name, because I didn't put a number. Square root of two parentheses, 0.34 times, you can tell I'm getting tired, right? 0.66. I like to use that as I'm scattered anyway, but I like to use the fact I'm tired as an excuse. Over the sample size. Okay, now what was the sample size? 100. Yep. Yeah. I'm mixing them, aren't I? But that's okay. That's okay. Because I'm comparing it, I'm using it to give me the range of values that I might have. Okay, so 0.34 times 0.66 divided by 100. And let me see, square root, 100. I think it's right this time. What did it calculated. Okay, the standard error comes out to be 0.0473. Okay, so now I go back here and I calculate my t-value. It's equal to P cap minus P cap France, which is 0.34 minus 0.06, divided by 0.04. And it comes out to a t-value of 1.2. Now, how many degrees of freedom is this? Well, I don't know about that, right? The problem here is that really when I took this proportion, what happened here, I had 28 people that said that they smoked, and I had 72 people who said they didn't smoke, right? It's really two groups of people, right? Smokers and non-smokers. So it's a little confusing. What should I do with that? Well, the interesting thing is here is one of the rules that we use when we use proportions is that we only do them when they have a large sample size. In other words, if the total sample size is less than 30, we can't do it. Total sample size here is 100. There's another rule though. If any one of the samples is less than 15, in other words, not just 30, you can't have 5 people in one group, 25 people in the other group, in other words, for the proportion, but both of them have to be at least 15, right? So, and that's the case here. 25 is greater than 15, 72 is greater than 15. Both of them have to be greater than 15. So basically what this means is you're always working when you do a proportion with a large sample. And when we're what we are willing to call a large sample. So if you're working with a large sample, what are we willing to say? What are we willing to say about what we're willing to use in terms of a t-score? Well, we're not really interested in t. We're going to use z instead. Z is equal to 1.2666 or whatever that, yeah, right? We're going to use the z table whenever we work with proportions, because the rules make us work with big samples. We're going to compare it to the z table instead of to the p table. So now we have to determine whether a z-score of 1.2666 gives us a p-value greater than, less than 0.05. So I am going to go to my t-table, and my z-table rather. I don't even have it open. Look at all those windows. Aggress the Z. I know it's in that folder, but it's easier just to get to it here. And here's my Z table, and my score of 1.666. Is that what it was? Yeah, 1.266. Okay, let's find out what area that represents. 1.26. 1.20123456 represents about 89.5%. I'm going to call it 90%. So that means that 90% of the value, 90% of this distribution is to the left of that. So that leaves a tail with what percent in it? About 10%. Not only that, but since we're doing a two-tailed test, we didn't know it was going to be higher in France or lower. We have to actually double that for the lower part. So our p-value, our probability of being wrong, if we reject the null hypothesis, is 2 times 10% or 20%. Since that's not less than 5%, we fail to reject the null hypothesis that the proportions, even though it looks like it is, we fail to reject it. What's a good way to go back and do this study again and maybe get better results? Increase the sample size, right? And what does increasing the sample size do? It takes that number 100 and makes it a bigger number. And since it's at the bottom of this value for square root, it makes this a smaller number. The standard error is a smaller number. So when we divide p cap minus p France and divide by a smaller number, we get a bigger t-score. So if we get the same result, if we had gotten the same result with a sample size of 1,000, let me see what that would have done. If it were a sample size of 1,000, the standard error would have been 0.0149. And what would have our t-score been? Our t-score would have been 4, which would have been bigger than the critical value, and so on and so forth. Our z-score rather would have been 4. Okay? All right, so I'm starting to lose my voice, and you want to know something about online courses. The thing about online courses is that conventional wisdom, or whatever it passes for that with online courses, because this is very new stuff, is that it works best when you put together these little vignettes. You ever see the Khan Academy? like those little. This guy Khan has this thing called the Khan Academy, and he started up a number of years ago. Bill Gates got interested in it, and if you Google Khan, Kahn, Khan Academy, you'll see the guy. He has videos up and stuff like that, and he started by putting together little 10 or 15-minute videos for his niece or something like that, because she was struggling in algebra or something like that. And they got popular. People started hitting them on. Other kids started using them to learn. Bill Gates got interested in them, and he funded them, and so on and so forth. And it's turned into like a real thing on the internet. If you Google Khan Academy, you'll see it. But the conventional wisdom is, or the way most people view this, is that the best way to use online tools like this, online learning tools, is to have small vignettes instead of like a 2-hour lecture, like you just got exposed to now. Right? You do it in little segments, 10 minutes, 12 minutes, 5 minutes, 10 minutes, and so on and so forth. Which, when we do a strictly online version of this course in the fall, we're actually looking at doing it that way. In other words, that's going to be fully online, that course. So at any rate, so at this stage, if you're not dead asleep or want to poke your eye out looking at this stuff, I'd be very surprised, because we've gone on. It would have been nice for me to organize this in smaller vignettes, but we have to do it we got a 3-hour window when we're all together. So I can't do it that way. However, you can kind of do it for yourself, because when this video is posted, you can scrub through it. If you need to go to what we did in, on the two sample test with unequal variances, you could just scrub to that part, ignore the other part, scrub to that part. If I can, if I had more time to do this, I would probably give you minute markers that, like, hey, if you're interested in single sample t-tests, go to the 5 minute and 10-second mark. If you're interested in this, go to the 30-minute, and if one of you guys wants to do that, for your fellow students and post it on the discussions groups, I'm sure they will reward you in kind someday, right? So you're all colleagues at some point in the future. So at any rate, that would be nice to do, because that way it's kind of like breaking it up into shorter segments where you don't have to look at it all at once. But I would suggest when you go back over this, don't plan on sitting here like you did now for 2 hours and trying to absorb all of this. Try instead maybe, let me do this first part when we talk about single sample t-tests. Then let me go on to paired sample t-tests. Let me go then on to independent sample t-tests, and so on and so forth. Let me look at the part on proportions and so on. So that's the way that I would view it. So we've been going for quite a while, so I'm going to call it a night as far as the lab is concerned. The lecture is pretty complicated. There's a little bit of other material on there in specific that talks about something called power and talks about sample size. I'm going to push that off until after the exam, so we don't have to deal with it on the exam, and so that we can squeeze in the chi-square and the other stuff, so we're a little bit better prepared for deciding what we're going to do on our projects before the exam. Okay, so I put into the homework. The homework assignment number 3 is available now, and it's mostly stuff for, I think, single sample t-tests. Yeah, 4. I put 4. I mean 4. Yeah, did I put both of them up? Yeah. Now that one I think is single sample t-tests and confidence intervals and single sample. I don't think it covers all of this material. I'm going to post either an exercise or another assignment that'll be due on Wednesday, which will be a brief one, but it will include these t-tests and so on and so forth. And I won't be able to assign a chi-square homework until after the exam, but I will ask you to. I will post a simple video or something like that, or example of it that you can take a look at, and I might ask you, a question or two on the chi-square test. Once you get a look at it, you won't be that intimidated by it. I guarantee it. This is more challenging than the chi-square test is. Okay, so good night, guys, and I suggest that if you have the energy, get started on the lecture video. If not, then like maybe you can hit it over the weekend or something like that. Okay, so good night. Oh yeah, look at that. They caught the error I was making there with the N. I looked completely past that.